but it's the encapsulation. There are many encapsulation methods there. We use the lid types, the glass lid. We use the glass lid. Some people use the metal lid. So metal lid, so this side we are not going to see any lights because it's opaque glass. We can use it, even the transparent glass, because this side is going to be the aluminium on the top. So it's not possible to see the light when we connect to the DC current. So it's a metal lid. It's a barrier layer they're using. Some manufacturers, they are using the barrier layer for the devices. It's an inorganic multi-layer, the organic ALD, and there are different type of material they use that to make the barrier layer. Then filling type, they just filling some resin type of filling and film type filling. So this method also you can cover your organic, I mean that all the films, because when you take it out, it's easy to dispose to moisture and oxygen. Then the device, it will work for 1 hour, 2 hours, then it will die quickly because it might be oxidized easily. Okay, now, so we just, there are two methods we using to improve the performance. One is ETL surface functionalizer that, we make the zinc oxide film, then we wash it with some different solvent. We found out that the hexane was the good one, give good performance. After we make the device, and we found out that the hexane. This is we do after zinc oxide films, spin it and dry it. That film we wash it with the hexane, and then we put other layers, quantum dots, and made the device, and we found out this. This is also the one way to improve the device performance. And another way, thermal aging, but some people are aging. Normally aging means they leave it, they keep it out for a while and characterizing. Then the different time, sometimes some quantum dots improving the aging when they aging, that device performance improving. Here we try thermal aging. What we have done, we use that furnace. That oven. This nitrogen environment oven. We push the nitrogen this and keep the device for 24 hours at 40 degrees. And actually, it's be baking at 40 degrees. Then 120 degrees also we done it. I will show some results later this lesson. Okay, we now some SEM measurements for this, the hexane was. This is 120 degrees after hexane was. How is it was? And the contact angles. If you look at the contact angles, actually, this is the film at 120 degrees. It was 28 degrees. Then we use toluene wash, toluene solvent to wash, that it went to 37 degrees. We use the hexane wash. Here is 23 degrees. So this 28 degrees, that surface improved. So that surface improved by 5 degrees by using this hexane. That's why our performance may be improved. So this is and the AFM, we did the AFM for this 120 degrees film. This is that the virgin film without wash that. It was roughness was 1.16 nanometer, but actually the after hexane was, we found one of them is 1.85 nanometer. This is just the quantum dots, zinc oxide. Then we put the quantum dots. We measure the roughness is 2.9. The top of the quantum dot film was 2.9. This is actually the zinc oxide. This film, we put the quantum dot on the top. Actually, the roughness is reduced to 1.95. So this is, end of the day, is going to talk about, isn't it? So this is because the roughness, this two film, actually the solution process films. So this 2.90 without hexane was, but with hexane was, it's improved 1.95 nanometer roughness. So this XRD, so this the zinc oxide, just the virgin zinc oxide film. It is the XRD. It was like that. This, and when we washed with the hexane, the crystallinity is improved. It was, I think, it's about 60% crystallinity. It's become 93% crystallinity of that film become when we wash with the hexane. This is absorption spectra of the zinc oxide, and zinc oxide virgin and zinc oxide hexane was absorbed more. This SEM of that zinc oxide and zinc oxide 120 degrees, and the hexane was that there's you can see that the film surface is better than this one. Okay, now we move to all solution process. Because we try to reduce the cost, so we need to find the way to make all solution process, because that vacuum thermal evaporation is expensive one, and it is not possible to make larger substrate. So first, whatever we used, then we tried to make some. See, these are small molecules what we have already used for electron beam TCTA. So we made some 0.58% ink, and this HTM40 also 0.5 ink and HCN. So here, but we have used for alpha and the TCTA, we use ethylene glycol dimethyl. I will show you the next slide why we use this one, and alpha NPB tetrahydrofuran, and this is easy to dissolve this TCTA and alpha HTM14 and HCN. These three we are talking, because these two already in solutions. So we just, these three we need to make the ink. So we just try this one and made the solution. And there are the next option, we use some polymers. Polymers, it is, we use PVK. PVK as an electron blocker we use there is easy to dissolve in 1,4-dioxane, and poly-TPD or TFP as HTL, we use dichlorobenzene and PXLene for the TFP, and MO3 is a phosphomolytic acid to be used, then we dissolve or disperse or dissolve in NMB, ethanol, that's 2:1 method we use to dissolve it there. Here, okay. Let's see what is the small molecules and the polymers, what's the difference, because we just, if you see the previous slide, here we just move to polymers from small molecules. So we just see what is the difference between this film formation, small molecules. So this solution processing make a crystallization, aggregation and an issue. It's a problem, but polymers, it will give a good film. There is no crystallization problem by this film formation. But reproducibility in synthesis, because small molecules, we have a better reproducible problem. We don't have any problem for synthesis and making small molecules. But here there are a problem challenging a reproduce molecular weight and polydispersibility impact processing and device performance. So there are issues there in polymers for this reproducibility. And purification, there are already established methods for sublimation there for the small molecules, but polymers purification is another challenge. Okay, what is the problem, this multi-layer from solution processing, I mean solution fabrication, the solution processing fabrication. So there are, if you see that ETL, we just coating the ETL, so we just, our ETL is zinc oxide. Then if we put emissive quantum dot, if it washed away this one, look at this ITO, then EML, we try to put emissive, but this one is white off because it the solvent dissolved this layer. So this is the one of the problem we have. Another problem, reduce the thickness of the layer, but we need this thickness, but it is reduced by this solvent. So it is mixed with it. Should be avoided when we use it. That is the problem we have, solution processing, I mean, multi-layer solution. So if we has overcome with this one, then the next one, this needs to be overcome by, so we need to find a way to overcome this both off or reduced and mixed. Shouldn't be happen when we make the films. So these should be like all the films, what the thickness we need to make it. That is our objective here. So this is how to be overcome this problem. We need to use orthogonal solvent. Orthogonal solvent means dissolve only the upper layer. So which layer we are using, that layer can be, that material can be dissolved in that solvent, not the previous one. So we need to find the way to stop dissolving that previous layer, previous material. It shouldn't dissolve. So we need to find the right solvent for that. That is the issue there. Or we need to use some cross-linkable material. Cross-linkable material, what will be done, it's cross-linked with heating or UV light radiation. It will link with the previous one. So it can't be dissolved. So it cannot be dissolved by the solvent which we are using that. Next, so this method we used. How do we find that? This is I'm just going to show because we're trying the GCT at top of the quantum dots, red quantum dots. Because these two layers we don't have any problem. We already established that. So GCT we are going to try with that. So how do we know this GCT film is the solvent is not disturbing quantum dots? So what we done? So this is it. Probably it's a small, but the red one is underneath of the green spectrum. So this is UV absorb. We made the film and the quantum dot films, and we run the absorption. Then we washed with the different solvent. We found out these three solvent: one copper dioxane, cyclohexanone, ethylene glycol dimethyl, not disturbing this film, the quantum dot films. So it is potential solvent to use to dissolve the TCTA. Then this is a TC, and the absorption we run with the TCTA thin film, vacuum thermal evaporated film, and the TCTA with the cyclohexanone is more or less that the shape and that the absorption is same. We found out, so we can use TCT as a solution process with solvent cyclohexanone. Then the next one, we use alpha NPB, HTM14, we couldn't find any solvent to dissolve, so we just use alpha NPB. So there are a lot of solvent can be dissolved, the alpha NPB, but when we do the same way, so we make the TCTA film and we use this different solvent, but you can see this all the fully washed off, except N-hexane is 2/3, and this methanol is half, and isopropanol. So there is no potential one we found because most of the film is the right thickness. We couldn't get it because even the shapeness similar with alpha NPB, BT, and this, but still that disturbing the previous TCAT film, any solvent, all of them mostly disturbing. So it is not possible easily to the small molecule to use solution processing. Then that's the next possible method, cross-linkable material, but we can make cross-linkable material with the TCT, alpha, and PB, but it's expensive method. So if we made it, we can use that photochemical or thermal way to the previous, TCT, if we make TCTA is cross-linkable material, then we can cure by photochemical thermal, then we can use alpha and PP. It won't dissolve the TCTA, but that is very expensive. You know, the method we got from there. We tried to make this one. It's very expensive, so we given up to make this one. Okay, there's another method, another publication we found cross-linkable alpha and beta, because even if we couldn't make, if we are not making this one, it's not possible to make it this one to go through. So we reduced this, but we made some devices, but it's not give a good performance for this. Then option 3. So this option, the polymers we can easily do, because polymers we don't have any problem. So this is I'm going to option 3, which is we can use P dot PMA phosphomultiplic acid and as a HIL and poly-TPD, TFE. PVK we can use a HTL here, because PVK can be electron blocking layer, because here we can use that poly-TPD and TFE we can use HTL. Then quantum dot zinc oxide. This is the conventional model. It is that most popular one. Most of the people use it. We can make it. We can make a good device, but still the semi vacuum, I mean, our inverted device structure very difficult to make by this method. So I am moving to the next one, is characterizing the devices. So this is important. Making device is one side. Is another side. We need to show how is it work, that device. That is only the selling point. So this what we are expecting, this our brightness and performance of the devices. So brightness is one side, and performance, I mean performance characteristics about we are going to see the different characteristics about these devices. So one is the electrical characterization. Electrical characterization is mainly the current efficiency of the device, then the power efficiency, and external quantum efficiency. These three, the way that we need to get higher value, then we can easy to tell any manufacturers we can make. We have this value of these numbers of efficiency and external quantum efficiency. Then they will look for us to. They like to get from us. Otherwise, we can't do anything. But we can do only the research on it. And also our research, we need to improve these ones. That is, we are looking for. And that optical characterization. So optical characterization is the quality of devices. This is the brightness. This is the quality. So the quality is the chromostatic coordinates, X, Y, that we will see later that. And the correlated color temperature, this we are looking for the cool white or the warm white. This is for the lighting purpose. And the color rendering index. These for the optical characterization we look forward from the devices. So this is some this is what is a light. This is just a definition of that. So I'm not going through this too deep. For this is visible region, you know, this between 400 to 700. We are looking forward that, and you can use this measuring the brightness using spot meter. Spot meter only the speed and accurate. This only doing the 0.1 is the spot meter. The imaging meter is where we normally use. This one is taking some 2D measurements, some particular length and width to measure, make the average measurement for this photospectrometer. Now that this is all mostly definition. So this is lumen candela. So what is the candela means, and what is the luminance means. So we are looking for the luminance. We are measuring candela per meter squared. I am focused on this one. So this is luminous intensity per unit of area at a point of given surface. So, okay, this is the thing we are looking for, this unit and the luminance. This is, we talk about, that's the brightness of the device. Okay, now the current efficiency, which is one of the electrical characterization, that how we calculate the current efficiency. Current efficiency is that the luminance L divided by the area, that the current density. So the luminance versus divided by current density. So current density. So we can put that surface area is on the top. Is I over. We can J is I over S. So it's going to be luminance time surface area of the current. So if we have a 3 millimeter time 3 millimeter surface lighting area, we using some 2 milliamp current, so we can just the brightness. If we know the brightness, we can calculate the current efficiency. So this the next one is the power efficiency. Power efficiency is that that's another device performance. This is the ratio of the optical flux to the electrical input, conserving current efficiency at an applied voltage. Vt is the given by equation below in unit of luminance per watt. This candelabra amp, this is a luminance per watt. So this some this is we have already we set up that this if we measure the voltage and voltage current and the luminance, then we can calculate the power efficiency. So this is all the theory for the power efficiency. And external quantum efficiency is, this is also this theory, we have already set it up in there. So this is the ratio between the number of photons emitted from the surface of the device and the number of injected electrons. So the quantum efficiency, this is external quantum efficiency. Internal quantum efficiency is in the coupling efficiency is that, yeah, then internal quantum efficiency is defined by this one. This is the depend on the quantum yield, photoluminescent quantum yield also is necessary for that to calculate this external quantum efficiency. There's another method, another people using another method of external quantum efficiencies. Okay, now this optical characterizations is a chromostatic coordinates. You can see the coordinates, you can see there from 0 to 0.8, here 0 to 0.9. So this normally this NTSC and the REC 2020, I have talked about application on Monday. So this is the color range, the NTSC system, the display they need if you want to use it for the OLED display here. You can see that, and the green is somewhere there. This is the OLED, and that QLED was, yeah, I mean NTSC, and that REC 2020 is here. And this this for the white. And correlated color temperature. There are temperature also. You can read some CIE diagram, the chromostatic coordinates diagram. So there are temperature, but we are looking for the white normally between 3000 to 6000. There are mixed color, but white is somewhere is a cool and warm white are there. And color rendering index is the measure of light source reproduce its environment colors, quantify how different test colors appear when illuminated source compare. This is, we are not borrowing too much because we will get it from our spectrophotometer. So this is our, we have, this is a Minolta photospectrometer. Then it is connected to our computer. So if we can get this, all the details we will get there. We mainly, this is that luminance, what is the luminance brightness. This is 180